Hi class, welcome to chapter 3. We're going to start with chapter 3.1, quadratic functions and models. So I said in the last video, chapter 3 is pretty important. Polynomials are important in general. We use them pretty much everywhere. They're our favorite functions next to exponentials. So we're going to really talk about how to deal with polynomials in this chapter. Again, very important. It transfers over for the remainder of the semester and directly into your calculus 1, 2, and 3 courses. So the stuff we're going to talk about now, the better you're familiar with it, the better you'll be. Okay, so we'll start off with the second most basic polynomial, which is the quadratics. The first most basic is the linear function, right? It's a first degree polynomial. So today we'll talk about second degree polynomials. And then any degree after that, 3 and above, we really just talk about in a general sense. So we have a lot of information about lines. We can talk about their slope, how to find the slope, how to find parallel, perpendicular lines, all these kinds of things. When it comes to quadratics, quadratics are much more broad. There's a lot more information to cover, which we will cover in this section. And then once we get past that, we stop talking about, oh, this is how we deal with cubics and 4th degrees and 5th degrees. We really just, at that point, talk about how to deal with polynomials in general, right? So for first and second degrees, we get very specific and very in-depth with how we analyze these functions and how we deal with them. Everything after that, we just talk about in general, right? How do we deal with an nth degree polynomial? So now we're going to talk about quadratics. We've talked about this a little bit in chapter 1 as part of our review. So now we're going to really kind of get into it. So we're going to keep things pretty general for the most part. We will have a very nice example at the end, but we're going to keep things more generalized in how to deal with quadratics overall, right? So there are 3 forms of a quadratic function that are important to us. The different forms have different uses. There's times when one form is preferable over another. Depending on what we have available to us, we want to be able to use any 3 of these forms. Now, with that said, we also want to be very comfortable in being able to go from one form to the other. Okay, so there's 3 forms to go between. If I have one form, I should be able to get to any of the other 2 forms. Okay. So the first form is the standard form. Okay, this is just the standard form of a polynomial, ax squared plus bx plus c. This is probably the most common form of a quadratic that you're used to seeing. Okay, the next is its factored form. Generally, when you see a standard form, the most generalized question that they ask you is, hey, factor this thing, right? So you guys are pretty familiar with the factorization of a quadratic polynomial. Again, we covered that pretty in depth in chapter 1. So in order to go to standard form and to factor form, you're really just going to factor, right? If I want to go from factor form to standard form, I just multiply this out. Okay, so again, remember that m and n are the zeros of this function, right? And then the third next most common is the vertex form, right? So these are the 3 forms. So vertex form is very useful. You should recognize this, right? When we want to graph things, you can see all the shifts and the translations that are going on to the standard form. If this is our standard form of a polynomial, we would like to be able to put it into vertex form, because then we know what the amplitude is. We know its concavity. Does it go up? Does it go down? Where is its vertex? How is it shifted left, right, up, and down, right? So that's the benefits of the vertex. The vector form lets us know the zeros, and the standard form gives us some other information. We'll talk about all 3 of these things independently, okay? So again, the important thing is, how do I go from one to the other? Well, from standard to factored, you have to factor, okay? From standard to vertex, you have to complete the square, right? So we covered this as well in chapter 1 and in chapter 2, okay? So if I want to get from standard to either of these 2 forms, I have 2 different options. Okay, so now you might say, well, how do I get from factored to vertex? Kind of have to go back a step. You got to go into standard form by expanding, okay? and then complete the square. If I want to get from vertex form to factored form, same thing. I need to go to standard form and then I can factor. Okay, so if you're already in a factored or a vertex form and you want to get to one of the others, right? So if I want to go from factored to vertex, I gotta follow the arrows, right? So from factored to vertex, I have to expand and simplify and get back to standard and then complete the square. If I want to get from vertex to factored, I got to do the same thing. I got to expand this out and simplify to standard form, and then I can factor it if it's factorable. All right. So following this diagram will allow you to get from any one form to the other. Right. Now, again, standard form is standard because I can go to either of these two. But if I'm in one of these, I have to backtrack to get to the other form that I want to get to. All right. So here, if you notice, A appears in each of these forms, right? B and C does not, M and N does not, H and K does not, but A does. And A is the exact same value in all of these. So if I have a standard form and whatever, if this is 2, in my factored form, this will also be 2. In my vertex form, this will also be 2. Okay. So the A value does not change across these values. Okay. So let's talk about standard form. Right. We're going to talk about each of these one at a time. Now that I know how to get from one to the other, that's great. But we want to talk about these in general. So for my standard form, ax squared plus bx plus c, there's certain things that this does for me that the others don't. Okay. Same is true for the factored form and the vertex form, which I touched on briefly, right? So the good thing about the standard form is that it lets me know what the y-intercept is. That's really the only thing it does, to be honest with you. So if I plug in x equals 0, so meaning I'm on the, I have no left and right movement, I'm only moving up and down, all of this goes away and I'm left with C. Okay. So again, this is the form that is presented to us most often. Okay. And it lets me know what the y-intercept is. If I plug in 0, all of this goes away and I'm left with this. So that means that 0C is my y-intercept, or what we like to call the initial value if we're in an application problem. Okay. So when I have factored form, x minus m, x minus n, this tells me what the zeros are on the y-intercept, right? So again, if I set this equal to 0, that means that I can use the multiplication property of 0. So this either has to be 0 or this has to be 0 when I have my whole equation being 0. So I can set either one of these equal to 0, right? So x minus m equals 0 means x equals m. X minus n equals 0 means x equals n, right? So the factored form tells you what the zeros of the quadratic are. If I plug in m minus m is 0. If I were to plug in n here, n minus n equals 0, right? We covered this a little bit before as well. So the factored form is nice because it tells us when my output of the function is 0. Here, this tells me what my starting value is, my initial point if it's an application problem. Okay. In the vertex form, we should remember this from chapter 2. It gives me all of my translations. It tells me how much up I move, how much left and right I move, and if I have any sort of change in the amplitude. This tells me where the vertex is. Okay, it gives me the location of the minimum and maximum values. Okay, the location. Okay, so not the actual value. It helps us to find the value. Actually, it does tell us the value because K is the max or min value, right? But it also tells us the location of the max min. What X value, what input do I need in order to reach that max? Okay. And then the actual maximum value or minimum value is the value of K. So it tells me where the max or min is at, and it tells me what the value of the max or min is at. And notice I plug H in, right? It's the address of the max or min. When I plug in H to my function, it tells me what that output is. Okay. So now let's do a graphical analysis. We'll use the graphs we'll use our general form, our standard form. Okay, we're going to use our standard form here to analyze the graph of a quadratic and come up with several useful equations that you should already be familiar with, but maybe not so much. Okay, so these will be very, very useful for the remainder of this course whenever you come across a quadratic function. Okay, so let's start again with the standard form of a quadratic. F of x equals ax squared plus bx plus c. Okay, and a generalized quadratic graph. So here we're doing one concave down. That generally would mean that a is negative. We could do this the other way as well. I just chose to use one that faces downwards because it's a little bit easier. You see this a lot in application problems too, because again, this models the flight of a projectile through space. So we'll just go ahead and use this one because this is the most common application that you'd come across. So that's why we'll use this instead of the one that is concave up, right? So where the opening of the bowl faces upwards. So here we're going to have concave down where the bowl faces downwards. So the easiest thing to find with the standard form is the y-intercept, right? So we're going to take this, we're going to find the y-intercept, which is here, right? That's where my graph crosses the y-axis. So when x equals 0, I get a value out of c. Okay. F of 0 means that I plug in 0 everywhere for x. So a times 0 squared plus b times 0 plus c just gets me c, right? Plus c is c. So for the graph, this is what we have, right? I have my same exact graph. I'm never changing the graph, right? I'm just going to start labeling things as I do math. So here, this point is 0c. The next thing that's easy for me to find is the other point, the symmetric point to this point. So if I draw a horizontal line across this line, I have an output of c at another point. So this symmetric point means I have a secondary output of c. So how do I figure that out? Well, this is my function. This is when my function is equal to c, right? It has an output of c. This is the other point where my function has an output of c. So what I'm going to do is I'm going to take my function and I'm going to set it equal to c. Okay? So again, the next thing we can do is find the symmetric point on the graph, or when my function equals c, right? What are the two times? There's 2 points, 2 different inputs, because it's not one-to-one, where I have the same output. So I set c equal to my function, and then I solve. So easiest thing is to subtract c from both sides, okay? And then from here, we have a common factor of x, okay? So I can pull out x, and now it's factored form. So this is true, it's equal to 0 when x is 0, which we already know, oops, okay? When x is 0, I get an output of c, right? Input of 0, output of c. I already know that. I have that point already. Okay. Here, if I take this and set this equal to 0, I get x equals negative b over a. Okay. Set this equal to 0, and you get negative b over a. So one point I have, this is the secondary point where I have an output of c. Okay, so again, one of these points are plotted already. 0c is already given, right? It was already found. That was the easy one. So that means that this is an input value of negative b over a. Okay, so when I plug in negative b over a, I get out c. So I have 2 points, okay, 2 symmetric points. So the next thing we're going to do is use these 2 points to talk about my next point, right? Quadratics are symmetric, okay? They're symmetric across the middle of the parabola, okay? The middle of the parabola is where the highest or lowest point occurs. So if I can find where the middle of this is, I can then use that to find the highest or lowest point. Well, if these 2 points are even distance from the center, right, from here to here is the same as here to here, that means I need to find the midpoint. Okay, we talked about midpoint before, so we will use the midpoint formula to find the center of my parabola. Okay, So again, now that we have two symmetric points, we can find the center of our graph where our maximum or minimum is located. So using the midpoint rule, we have that the x value of the midpoint, which is the same as h, okay, is halfway between the two x values, or the average of the x values. So that's negative b over a, the furthest output value, okay. So the average of this input, which is 0, and this input, which is negative b over a, okay. So again, this is just negative b over a times 1/2 gives me negative b over 2a. So the h value is negative b over 2a. Okay, so that's my location of h. It's halfway there. Its value is negative b over 2a. That's the value of h. That's where the center is always at. It's negative b over 2a. Okay, now that I know where that is, if I plug this value into my function, that's the value of the output, right? Input, output. So I need to plug this value of h, negative b over 2a, into my quadratic to find what the max or min value is. So the max or min value is located at h, so k is the same as f of h. F of h is the same as f of negative b over 2a. So I plug negative b over 2a into my quadratic. So again, this is my x, right? So a times x squared plus bx plus c. So I'm going to square my input, and I'm just going to simplify this down. Once I simplify this down, I'll have a formula then for k. So first thing I'm going to do is square this. So I got a b squared of 4a squared. B times this gives me a negative b squared. Okay, because it's a negative b times a positive b, so it's still minus b squared. Here, this a and this a squared get to cancel. So I have 4a, b squared on top. This is still b squared over 2a. This is still c. So now I would like to combine my terms all into one thing, right? So my common denominator, right, my LCM of everything I have so far is 4a, because I have a 2a. There's a 2a in here. There's just an extra 2, which is how I have 4. So 4a is the common term. So here I don't have to do anything. Here I'm going to multiply top and bottom times 2. Here I'm going to multiply top and bottom times 4a. Okay. So this b squared gets left alone. Remember, this was top and bottom times 2. So that's my 2b squared. Here, top and bottom, I had to multiply times 4a. So that's how I got 4ac, common denominator of 4a. Okay. Now I have b squared and I have minus 2b squared. Those are like terms. So I have negative 2 plus 1 leaves me with a negative b squared. Okay. This notation is a little weird, so I'm going to change these around so that I have a positive minus a negative, right? And so I have 4ac minus b squared over 4a is my max value. That's my k. My input is h, which is negative b over 2a. So I plug in negative b over 2a. I get out 4ac minus b squared over 4a. So I have my first point, 0c, right? My initial value. I have its symmetric point, which is negative b over a. I use that to find my center, where my max or min lies, which is negative b over 2a. I plug that into my function, ax squared plus bx plus c, to get out what my maximum or minimum value is, which is 4ac minus b squared all over 4a. And so there's really only one thing left for us to label here, okay, which is the zeros. I don't know where this crosses the x-axis, okay. So the important parts so far are this 0c, this h and k. This we probably never actually use, but it helped us to find the h, which we used to find the k. So this point was really just helpful for us, right? It's not something that's used very often, but that does help us to understand the symmetry of the graph that we have, okay? So next we need to find the x-intercepts, okay? So the x-intercepts are when we set the equation equal to 0, right? This would be very, very easy to find if we had this factored already, okay? This ax squared plus bx plus c. But we can't really factor unless we know the values of a, b, and c. So what we do instead is we use a method that most students don't like that allows us to find the zeros always, right? Which is to complete the square, okay? So we already know that when we complete the square, we get the quadratic formula. So we have x equals negative b plus or minus square root b squared minus 4ac all over 2a. So remember, this is two values. This is a plus and a minus, okay? So when we graph these, we have these two values. Now here you see me, I put the plus form, and here I put the negative form. It really actually depends, okay? Because if my values here, really just depends on what the values are, to be honest with you guys. So for this case, this is what it would look like. When the parabola is concave up, the negative is actually the smaller and the positive is actually the larger. So really you just plug in your values and you'll get two values out. Your smaller one is the first one, your larger one is the second one. So here, just really watch this. This isn't always the smaller one and this isn't always the larger one. You really just kind of have to plug your values in. The smaller one is first, the larger one is next. So please be wary of that. Okay. Let's do an example. Okay. So Professor Williams' mind melting company melts the minds of your foes, right? The company isn't doing as well as you think. You think more people would want their enemies' minds melted, right? They'd like to invest in some advertising to increase their income. So we're going to let x represent thousands of dollars, right? And f of x equals negative 1/4 x squared plus 3x plus 1 represents the monthly revenue, right? So revenue is the money that you generate, okay? So the output here is in thousands of dollars, okay? Again, in thousands of dollars. So to reread this so it makes sense, let x represent thousands of dollars. So input is thousands of dollars. This function represents the monthly revenue in thousands of dollars of the company based off of investing X thousand of dollars in advertising. So basically it's saying that if you plug in, if you invest X thousand of dollars, then this is the amount of money you're making in thousands of dollars. Okay. And this is all based off of advertising. So we have a couple of questions. Okay. A is, how much is PWMM, the Professor Williams mind melting company, making a month without any marketing at all? Okay, so if I don't invest in marketing, which is what this company represents, this function represents the amount of money I make if I invest X thousand of dollars, right? So if I don't invest any money, how much am I making? Okay. B is, how much would Professor Williams invest? Should I invest in marketing for my mind melting company? And what is the maximum amount of revenue Professor Williams can make? So these are the four questions that are very, very standard for an application problem of quadratics, right? So the last being, what amount of money invested results in a negative return, meaning that I'm losing money. I'm investing more money than I'm making. Okay, so A. How much is Professor Williams' Mind Melting Co. making a month without any marketing? So this is an initial value problem, right? So if I invest $0, how much do I make? Well, that's very straightforward. All of this becomes 0. That's the y-intercept, right? So without any marketing, I'm only making $1,000 a month, right? So f of 0 equals 1. Remember, this is in thousands. So that's $1,000 a month without any advertising. Again, that's my revenue, right? So that's how much money I am bringing in. So that does not include costs and overhead and all that kind of stuff. That's just how much money I'm bringing in every month. Okay, so revenue is the money you generate. B, how much should Professor Williams invest in marketing for Professor Williams' Mind Melting Company? So how much should I invest? Well, I should probably invest the amount that will make me the most money, right? That makes the most sense. So, the amount that would bring me the largest return in revenue is wherever the maximum is located, right? So I need to find that value of h, okay? So h is negative b over 2a, okay, which is negative 3 over 2 times negative 1/4, right? So again, if we come back to our equation, b is 3, a is negative 1/4. So here we have negative 3 over 2 negative 1a. So that gives us 6, right? Because this gives us a negative 1/2 multiplied by the reciprocal. That turns into 6. So the max I should invest is $6,000. Okay, that's the best investment. That gives me the maximum return out. So part C is the flip side of that. What is the maximum return? Well, I can use the formula that we had, or I can just plug in 6 to my equation, whichever is going to be easier. So remember, we had this formula for the max output, so I can plug in my A, B, and C here, or I can just plug in 6 to my equation. Either way, I should get the same value out. Here, this can be, it looks like it could be rather tricky because of all the fractions, but my A is 1/4, so that actually just cancels out, right? So this gives me a negative 1 minus 9, so that's a negative 10. And this is a negative 1, so that gives me a positive 10, right? It's basically negative 10 over negative 1. Very, very easy. Positive 10. So when I invest $6,000, I generate $10,000 in revenue, okay? Or if I wanted to do it another way, again, I can just plug in 6. This one actually seems like it's less or more work, possibly not. So this is going to be 18 plus 1 is 19. This is going to be 36 divided by 4 is 9. So this is negative 9 plus 18, which is 9 plus 1 is 10. So I get the same thing out. It really just depends on which one you think is easier to do. Okay, so regardless, the max revenue is going to be $10,000. Part D is what amount of money invested results in a negative return. So when am I going to stop making money, basically, right? So negative return means we begin to lose money. So the cost of running the business no longer brings in a profit, right? So I'm investing more money in advertising than I'm making. It doesn't work out too well, right? So this is going to happen when f of x equals 0. So when I get 0 out, anything past that now loses me money, right? So since our model is not easy to factor and completing the square can be time consuming, I can complete the square, but we have the quadratic formula, so we're just going to use the quadratic formula, okay? So when I plug in my B, my A, and my C, this is what it looks like. Negative 3 plus or minus, this will be 9. This will turn into a positive 1, so this will be square root of 10 here. This will be a negative 1/2. So 1/2 just doubles everything up here. So this turns into a positive 6 because this was negative. And then this will be a 2 root 10. And this will just switch signs to minus plus. But it doesn't really matter because minus plus and plus minus here is the same. They're both positive. It doesn't really change anything, right? So using the positive values, because negative values don't make sense in the context of this. If we're looking at zeros, our graph will represent something like this. Let's go here. Okay, our graph looks something like this. This is what happens when I don't invest any money, right? I'm looking for when I'm going to stop generating revenue because I'm investing all of my money. Anything past that, I'm now losing money. Okay. Here, investing over this way doesn't make sense because I can't invest negative money into my situation. It doesn't work that way, right? So anything that's negative input-wise doesn't make sense for my application. Okay, so I only have to consider the positive portion of this when I get to this value. Okay, so I just need a 6 plus 2 root 10. And again, I love exact values, you guys. You know I do. by the time you've seen this, you've probably been knocked down points. However, this is an application problem. I have no idea what 6 plus 2 times root $10,000 is. I have no idea how much that is. I know it's more than 6,000, but I don't really know. So application problems, decimal forms, okay? Actually give me an approximate value. We're talking about money here. Tell me how much money I'm making, okay? Or how much money is the max that I should invest before I start to lose money. Don't give me this as an answer. Again, if it's just the math problem with no context behind it, yeah, perfect answer. Application problem, however, tell me how much money this is, right? So 12.324553, that's $12,000 and some change, right? So let's put this into money, right? So the proper decimal place will be at the 55. This last 5 here rounds this to 6. So $12,324.56. Anything more than that, I'm going to be losing money. If I invest exactly this amount, I get $0 back. I've just took all the money I've made and thrown it into advertising. Okay. So once I invest more than this, I will be past the break-even point. This is where my break-even point is at. Okay. So we're spending all the money that we make. So as a graph, this is what it looks like, right? My initial value is 1,000. Anything below that doesn't make sense. This is my break-even point. Anything past that, I now have negative outputs. My max is at 6, right? And my max output when I invest 6,000 is 10,000. Okay? So y-intercept, maximum value, break-even point, right? And that's my graph, you guys. That's how quadratics work.